So thank you very much for coming along. It's a fantastic turnout, and unfortunately people are going to have to stand by the looks of it, I'm sorry. I'm Brian Patton, I'm the Civil Defence Manager for Marlborough, and I've got a couple of my team here. There's Gary Spence out back and Catherine Coates, who handed out some of the pamphlets. We've also got Charlotte Wood from Neighbourhood Sport here, so afterwards you're very welcome to bail up Charlotte as well. One of the things that we always say about a big event is actually you're not going to see Gary, Catherine and I. Civil Defence is going to be trying to coordinate the whole thing, so you won't see us, but what you will see, hopefully, is your neighbours, and it'll be your neighbours who are your first responders. And so we're working closely with Neighbourhood Support in recognition of that. So catch up with Charlotte at some stage. We've got a couple of presenters today, and so the running order is going to be, we're going to hear from Alice, and Alice is the AF8 Program Lead. So she's the only full-time employee of AF8. So the 6 civil defence groups in the South Island fund Alice and the role that she does. And we've got Kate Clark from GNS Science. So Kate's going to give us a rundown on the earthquakes and touch on the Hikurangi fault perhaps. And then we'll have a bit of an interactive session where we're going to open the floor, and as many people as wish to, you're very welcome to ask any questions, and between the three of us and maybe Catherine or Gary, if I get really stuck, we'll see if we can answer your questions as we go through the evening. So hopefully we'll wrap up at about 9 o'clock. If we haven't, what we might do is pull the pin anyway, and if you've still got a question, the 6 of us will be hanging around, and you're very welcome to bail us up after that. So all good. All right, some of the housekeeping rules around the place. The first option to get out of this place, if we need to evacuate the building, is through this entrance here, not through the entrance you came in. So go through here, keep turning left around the building, and the car parking area that you came in, the front door there, is the assembly point. Everybody knows what to do if we have an earthquake while we're in here. Drop, cover and hold, and if you can't drop and get back up again very easily, I suspect you just go into a bit of a turtle position where you are and hold on tightly. Because there's a lot of us that once we get down, we're not in a good space. And there's nothing going to fall on your head, so you'll be fine just curled up in your chair. If you need a pit stop, just go back through, you've all walked past them actually, just go through the door there and turn right and keep wandering down there until you see whatever sign on the door you're looking for. Have I forgot anything? So we're going to be taking some pickies from the back, so that won't be, hopefully we won't be identifying anybody apart from the speakers, and Alice is recording us doing this, hopefully not this bit, but Alice keeps it safe and we'll start recording that. Anything else? I think that's all off the top of my head. Yep, sweet as. Alice, can I hand over to you?
Thanks, Brian, and thank you everybody. Soon, Brian, not be blinded by the light. Thank you everybody for coming out tonight. Sorry we don't have enough seats to fit you all in, but it's awesome to see such an interest in both the Alpine Fault and the Hikurangi Subduction Zone, and obviously most importantly what we can do to be better prepared for this plate boundary that we live on. So I'm just going to give you, let's go up higher. Closer? Yep. There we go. Okay. So I'm going to give you a little bit of an overview of what AF8 is. It's going to be short and sweet before I hand over to Kate for the real information that we're here for today. So AF8 stands for Alpine Fault Magnitude 8, in case you hadn't realised that yet. And we are a program of scientific modelling, response planning and community engagement. We are a South Island project. We are a collaboration between the 6 South Island civil defence groups here. And as you can see, the Alpine Fault is a shared hazard amongst all those groups. It is in fact the largest natural hazard here in the South Island. And when you look at a map like this, you start to think, well, this isn't something that we should be preparing for in isolation. This is something we should be preparing for together. And now to prepare for something quite this big, we also need multiple domains of knowledge or multiple ideas, multiple experiences to draw upon. And this is kind of what that looks like. So we have our research partners, such as Kate, Kate's from GNS Science, and we also work in with our councils, our policy, our practitioners, our community. We all have a part to play in preparing for an event of the size that we're talking about here, and there is a lot that we can all do together to get ready for that. So I will now hand over to Kate to talk you through the science behind this.
Thanks, Alice. Thank you everyone for coming along tonight. It's amazing to see such a big turnout. So I will be talking about earthquakes, specifically here, mostly referring to impacts around here in the Marlborough region. But we are at the plate boundary crossroads between the Alpine Fault and the Hikurangi Subduction Zone. So Alice has given a bit of background about Project 8. I'll be mostly talking about the Alpine Fault, and on that mostly talking about past earthquakes, which is how we forecast what future earthquakes will be like and when they may happen. I'll talk a bit about what we anticipate the future impacts of an Alpine Fault earthquake will be, and near the end I'll touch a bit on some of the Hikurangi Subduction Zone research and specifically look at the relationship between these 2 major plate boundary fault systems. So a little bit about me. I'm an earthquake geologist at GNS Science. Been there for about 15 years. I study past earthquakes and tsunamis that have impacted the coast, which is a great job because I spend a lot of time at beaches. And I am lucky enough to occasionally work on the Alpine Fault. But you can see from these photos I spend a lot of time in the mud, searching for evidence of past earthquakes and tsunamis to help us understand hazards. So zooming out a bit, we're down here on the plate boundary, part of this massive plate boundary that goes around the Pacific Rim, also called the Pacific Rim of Fire, mostly for the volcanoes along much of the plate boundary. So yeah, at least there's no volcanoes in the South Island. If you're despairing at the end of my talk, there's no volcanoes here. There's a picture there that you've seen of the Alpine Fault, and I'll go into a bit more detail of that. So just check. So yeah, as I was saying, Marlborough's really at this sort of central zone between these 2 major plate boundary systems. So in the North Island, we've got this fairly simple scenario of the Pacific plate subducting underneath the Australian plate. And in most of the South Island, we've also got a simple plate boundary of the Australian plate sliding past the Pacific plate. And where they join, where they slide past each other, is the Alpine Fault. Marlborough is in here, in this kind of messy transitional zone between these 2 plate boundary systems. Many of the faults around here, like the Wairau Fault, just a few kilometres away from us, are part of the Marlborough Fault system, which is how the movement between the plates is transferred from the subduction zone onto the Alpine Fault. So as I was saying, the Alpine Fault is where the 2 plates slide past each other. We've got the Australian plate going to the northeast, Pacific plate to the south. There is a bit of an obliqueness here to the Pacific plate, so it's mostly sliding past, but also slightly crashing into each other. And that element of obliqueness is actually what is uplifting the Southern Alps. So we think in sort of your average Alpine Fault earthquake, you get about 8 to 10 metres of sideways movement here, and about 2 to 3 metres of uplift on this side of the fault. So that accumulated amount of uplift over millions of years is what has grown the Southern Alps of New Zealand. So mostly what it be talking about now is some of the science behind these quite scary headlines. So I'll be talking about what we base these numbers on, this sort of 30%, 75%, and why they've changed. So in 2012, there were lots of headlines when some of our research announced that there was a 30% likelihood of a large alpine fault earthquake in the next 50 years. And then just 2 weeks ago, more big headlines, even scarier, a 75% chance of a major alpine fault earthquake in the next 50 years. It's not that the likelihood of an earthquake shot up 45% in 9 years. That would be truly alarming. It's that the normal science process, we have more advanced tools, different methods, more people working on it, and just the normal process of increasing our science knowledge. This isn't necessarily wrong. I'll talk about this 30% still largely applies to the very southern end of the fault line. But the 75%, what we know now, applies to the central part of the Alpine Fault. So what we knew prior to about 2010 about past large earthquakes on the Alpine Fault, and when I'm saying large earthquakes, I'm sort of talking about things over about magnitude 7.5, earthquakes that are large enough to rupture the ground surface. We knew about 3 or 4 past earthquakes on the Alpine Fault because our main tool was just digging trenches across the Alpine Fault. So this is one of the trenches across the Alpine Fault. We just had a digger, scrapes away all the sediment, and we look at how these are offset on either side of that fault line. And this is a really effective tool for understanding the most recent earthquakes, but as you can imagine, you either have to go deeper to get older earthquakes, but they also become very overprinted by more recent earthquakes. So it's hard to, with any pattern, it's hard to sort of forecast what will happen next when you've only got 3 or 4 data points. In 2012, that 30% likelihood of a large alpine fault earthquake, it came from these studies on the very southern end of the Alpine Fault, near Milford Sound, these beautiful field locations. You've got the Alpine Fault going up here, and in 2 places, John O'Groats and Hikuri Creek, have quite large rivers that come out of the ranges, and the Alpine Fault here is actually going up on the other side. It's going up on the western side. So these rivers come across. When this fault ruptures, it blocks the river and a lake temporarily forms. So you get lake sediments being ponded up against the fault scarp. Eventually the lake fills up and you get it reverting to a normal river environment like you see today. So this had happened many, many, many times, and we either caught or could look at outcrops along these rivers to see this repeated pattern of the environment changing with each earthquake. Here's an example here of some of these outcrops along the river, and each of these sort of couplets of brown and light sediment represented an earthquake cycle. When we put all of this evidence together, it gave us this really long record, an 8,000-year record of earthquakes at this point on the Alpine Fault. So, a record of, when we put the 2 sites together, 27 past earthquakes, which at the time, and I think it still stands, as a world record for the number of past earthquakes we know about on any fault. And the important thing from this study was, a really long record for the first time. They were remarkably regular. If you compare this to many of the other sort of well-known plate boundary faults around the world, like San Andreas, this is like clockwork compared to most other faults. The average interval between these little, I should have explained each of these little black things, is an age distribution histogram, and here's the age, the time along, the time is along the bottom. The average interval between each of those earthquakes was about 300 years. So we could use that really long record to forecast the 30% likelihood of a large earthquake in the next 50 years. Except it's just for the southern section. We didn't at this time have information on the rest of the Alpine Fault, which, as you know, is very long. So the news just a few weeks ago came from lake studies. and these studies were led by somebody called Jamie Howarth at Victoria University. And it turns out lakes record earthquakes really, really well. So you can see this lovely southwestland lake. Currently, in between earthquakes, it's just quietly accumulating fine-grained sediment in nice horizontal layers. You can imagine if you shake that really strongly, all the sediment that's built up around the edges of the lake from all the streams and things entering that lake, it all just sort of slumps and sloughs into the middle of the lake. So you get this chaotic layer of sediment deposited in the middle of that lake every time there's a big earthquake. And then you get a whole lot of quite coarse sediment coming down because you've shaken these hills and they're full of landslides, and for about 50 years you get all this sediment coming into that lake. So these lakes record these cycles of sort of quiet sediment accumulating, large earthquake, everything, chaotic layers deposited, lots of sediment, and then it all reverts to sort of quiet conditions again. So Jamie Howarth, his sort of specialty, is lucky enough to go out on all these lakes, takes really long cores, analyses all the sediments, and here's a map of where each of those lakes were. So the good thing about this is that there's lakes everywhere along Westland, and what's key here is that he looked at lakes right along the central section, that yellow section of the Alpine Fault. So we're getting a much longer sort of spatial distribution of our data now from looking at lakes. And apologies for this complicated diagram, but it's basically the same as what we had before. Here's records from the southern end of the faults. There's earthquakes recorded in those wetlands by the valleys that gets blocked. And these are all of each of these 4 ones is the lake records. So you can see here's a record of 15 earthquakes in the past 4,000 years. So there's 2 advantages to these lake records. One is that they're right along the central section of the Alpine Fault, so we've got more spatial extent, but you can also really precisely date these earthquakes from the lake sediments because they preserve things like individual beach leaves, which can be radiocarbon dated. So we get really precise earthquake ages. Because we've got such a long extent of data along the fault line, we can start to understand where the earthquakes occurred and how much of the fault line actually moved or ruptured in each earthquake. We can use that information to start to understand fault behaviour. So, things like, is it always rupturing in magnitude 8 earthquakes, or are there smaller earthquakes? Like, what's the pattern here? We can start to put this information into physics-based earthquake simulators. I'll show a little video of that next. Basically, putting in sort of the geometry of the fault, how fast it moves, and looking at using physics-based sort of laws, looking at how the stress builds up, and then how earthquakes occur in response to that stress build-up. The nice thing is when we have a really precise, well-dated record like this, we can try and match it with the simulator. So if you've got really nice simulated models but nothing to test them against, they're a bit meaningless. But in this case, we can test these simulations against this geological record. And when they match, we can have a lot more confidence that our model is actually producing something that's worth sort of listening to and can potentially help us with forecasting the next earthquake. This is, just have to see how I can, do you know how I run this? I think it's just, should have my button. This is just a snapshot of one of these physics-based simulations. So the blue and the green, this is just about 2,500 years of earthquakes on the Alpine Fault at any point in time. It doesn't really matter. The blue and the green is the stress build-up in between earthquakes, and the rainbow-coloured are the earthquakes that occur. So we can run this model and see how the fault's behaving, compare it to our real-world data set, and we see a really great match to how this model is behaving and what we actually see on the Alpine Fault. So what we get from that revised earthquake record from the lakes, from the central part of the Alpine Fault, that's where this new number of 75% likelihood in the next 50 years came from. So that applies to this whole central section of the Alpine Fault. The reason it's quite high is because we have more frequent earthquakes on this part of the fault. So the recurrence interval along the central section is about 250 years on average over this 14 or 15 earthquake record that we have. So slightly more frequent. The revised likelihood on the southern section is about 38%, so that's gone up slightly from 30%. I think the recurrence interval from this new data is about 290 years on average between earthquakes. So these numbers are based on those earthquake records. From that physics-based simulator that I showed you, we can see that there's an 82% likelihood the next earthquake is going to be an earthquake that ruptures both segments of the fault, so both the southern section and the central segment. So there's an 82% likelihood we'll have most of the Alpine Fault rupturing in the next earthquake, just given the current stress state of it. And that earthquake, we can calculate from the length of it, is likely to be magnitude 8 or greater. So it's all good knowing lots about past earthquakes and forecasting the next one, but what we really need to understand is what the impacts are going to be. So this is a map of modelled shaking intensity from a large Alpine Fault earthquake. So there's a predictable relationship between the ground motion or the shaking intensity where you are and your distance from where the earthquake is. And this is what gives us these maps. We use ground motion prediction equations to develop these. So this is a map of an earthquake that starts in the middle of the Alpine Fault and ruptures both ways. So that's called a bilateral rupture. It's going both directions. And I'll talk a bit more about the rupture direction in a minute because it's quite important. It controls, it changes how you feel the earthquake at either end of the fault by quite a lot. For comparison to some recent large earthquakes, these two maps are at the same scale as that one. So the Darfield earthquake in 2010 affected most of the Canterbury Plains, and the Christchurch earthquake of February 2011 mostly affecting just Christchurch City. So you can see an Alpine Fault earthquake simply because of the length of this fault. The ground motion, the shaking intensities are going to be spread over a much, much larger area. Basically, the entire South Island will feel this event. AF8 has been developing different scenarios of what the next Alpine Fault earthquake might look like for their emergency preparedness activities. So these are just scenarios. They're based on sort of scientific consensus of what we think a credible earthquake would be on the Alpine Fault. So these are all magnitude 8 earthquakes. And I've got more slides that show these in more detail, but basically you see with each scenario we've got an epicenter down here rupturing to the north, one that goes from the north to the south, and a central section with that bilateral rupture. All of these will be felt across the entire South Island. The intensity, basically there's going to be very high intensities right along the west coast. The intensities that's felt on the east coast will vary a lot depending on which way that earthquake goes. This intensity scale, I see it's details about it down here on this poster. But intensity 4 is, you'll feel it, it'll be a gentle shaking. When you start to get to about intensity 6, that's when you feel it'll be quite hard to stand, things will be falling off the shelves, some furniture might be knocked over. And at 7, that's when you start getting some structural damage to things like unreinforced masonry buildings. At 8 and above is where you start getting some major and catastrophic impacts. So this is the north to south rupture scenario, where the rupture might start in the north and go to the south, and you can see relatively minor shaking up here in Marlborough, even intensity 4, so sort of weakly felt. Central rupture, if it starts in the middle and goes both ways, it changes how you feel it up here in Marlborough. So there is that sort of difference between the epicentre might be closer to Marlborough, but if it's directed the other way, it won't have such an impact. But if it's further south and directed to the north, it will have a larger impact. And this is the south to north rupture. So starting right down here in Fiordland and rupturing northwards. This is actually quite a lot. This scenario is sort of similar to the Kaikoura earthquake in 2016, and that started down here in North Canterbury. The epicentre was down at Waia, but it ruptured 180 kilometres along a series of faults up here. So the shaking in Ward, where that earthquake was sort of directed to, was much, much more intense than much closer to the fault down here in North Canterbury, simply because of the direction of the earthquake energy. This is a simulation by Brendan Bradley at the University of Canterbury. This is showing simulated ground motion intensity from that magnitude 8 earthquake that's going from the south to the north. So this is not how much the ground is actually going to move. These are just model seismic waves to look dramatic, but it does. What is quite useful in this is you're seeing the rupture time up here. So this is a prolonged event. It takes, it's a big distance, and it takes a while, many minutes, for that earthquake to travel along that fault. You'll start to see here, as the earthquake waves start getting into the Canterbury Plains, you start seeing all that amplification of the waves because of the softer sediment on the Canterbury Plains, and you get quite a bit of amplification and sort of reverberation, like ringing like a bell around that area because of those seismic waves and because of all that soft sediment on those Canterbury Plains. So this is heading further north, and yeah, you can see we're up to 3 minutes now. So this is a really long event. I think we're almost there, and it does, of course, carry on to the North Island. The model's just cut off here; it doesn't stop at the constraint.
So what sort of damage would that do in Wellington?
That's a good question. I don't know precisely. Yeah, it depends on how directed it is to Wellington, but probably similar to the Kaikoura earthquake. So maybe some major damage to poorly constructed buildings, but otherwise just quite long shaking. And yeah, it might affect different buildings depending on their height. So this is just summarising those shaking intensities. And they're
My brain is more severely affected than the further south.
Sorry. This area here.
Yeah.
I can't say precisely. I mean, it is, well, that's right close to the fault, but it's also probably similar to the Canterbury Basin. You've got a lot of run out there of gravels and alluvium from the hills, so you probably get amplification of the waves through that softer sediment.
Can you repeat the question so we can all hear it?
Oh, sorry, he asked why Greymouth is a red block, basically, why it's so badly affected. Sorry. Yeah, so here's the summary here. Intensity of shaking is likely to be about 6 to 7, so that's at that kind of hard to stand up, things falling off the shelves. This is probably about the level of shaking that people in Blenheim felt in the 2016 Kaikoura earthquake. So it will be prolonged, but not severe shaking. So sort of moderate shaking for many minutes. But yeah, similar levels to 2016. Just talking a bit here now about secondary impacts. So it's focused a lot the earthquake shaking, of course, that's what damages our buildings, but it also triggers a lot of secondary hazards or cascading hazards from that earthquake. So just one example of a cascading hazard is that the ground shaking causes a landslide. If the landslide goes into a river valley and blocks that river, then you then have the hazard of a flood, sudden flood, as that dam breaks. So there are it's not just about the earthquake shaking, there are likely to be a number of secondary or cascading hazards from an alpine fault earthquake. There's likely to be a long sequence of aftershocks, much like we had with the Kaikoura earthquake. Some of those might be large enough to be damaging in themselves. If there's something like a severe storm close to or soon after the earthquake, that's likely to be worse because of all the landsliding that's happened. And there is also the possibility of fire following earthquakes as well, which is harder to deal with, especially if all your water systems have been damaged by the earthquake. This map here is showing the probability of landslides across the South Island from that same event, that north to south magnitude 8 earthquake. So the reds, of course, are showing very high probability of earthquakes. The likelihood of a landslide, the likelihood of a landslide is based on proximity to the fault line and based on the steepness of the terrain. So steep slopes close to the fault have a high probability of a landslide. The further you get from the fault, less likelihood. It does depend on the slope of the land and distance from the fault. When you put the major transport routes, these are all the state highways in the South Island, when you overlay that, you can start to see that most of the main highways over to the west coast are going to be, there's a very high likelihood they will be impacted, probably shut by large landslides on those roads. The Bullard Gorge up here, slightly further from the fault, hopefully won't be blocked, but still very likely to have landslides on it, and maybe the quickest way into the west coast after such an event. The loss of roads is going to hinder the response and recovery to this event. And that, of course, we see it whenever there's a large storm as well, when the roads close on the west coast. It has a major impact on the economy as well. This is a similar situation for the electricity distribution networks. Here's the main transmission routes. Pylons and poles are likely to be damaged across the South Island. Transformers damaged. It's likely that many of the hydro dams will have to shut down to inspect all the turbines and that everything's still safely operating. The main transmission route to the North Island is quite vulnerable, so there is likely to be implications for the North Island as well from this. And of course, that loss of electricity will have implications in itself for all the communications after the earthquake. So, response and recovery from the earthquake, telecommunications will be essential. The loss of electricity could majorly damage our communication networks. This is why we're studying these things now, because now is the time to start building resiliency into all these lifelines networks, sort of our roads, telecommunications, electricity, water. We can't do it after the event, so now's the time to be building these things up to withstand a large earthquake. So this is just a summary of that alpine fault segment of the talk, shown through those long earthquake records, why we have such a high level of certainty that the next large alpine fault earthquake is very likely to happen, if not within our lifetimes, probably my children's lifetimes easily. The scenario earthquakes that have been developed for AF8, they're not exactly what will happen, but they're really useful for our planning purposes, because even if we plan for the worst case, it just makes us better off if it's a smaller earthquake. Widespread secondary hazards. landslides and things. We can't just keep focusing on the shaking because there's lots of other impacts that will happen. Likely that large areas will be isolated for some period of time, and communication networks are going to be severely tested by this event. And there's going to be a bit more talk on preparedness and so on at the end of this as well. I'm going to skip now to the Hikurangi subduction zone, so it's not necessarily a more cheerful story. Sorry.
Can I just ask you a question about what's happening going through Marlborough? You've got a major fault going up the South Island, which seems to disintegrate when it comes through Marlborough.
Yep.
Now, does that mean that we're going to get multiple smaller earthquakes, or are we likely to still have a big one as it comes through?
I'm going to get to that. Sorry, that man just asked what happens in Marlborough, whether you're likely to get something very large going right the way through or lots of smaller ones, and I will come and address that soon. Marlborough is here in between the Alpine Fault. All that movement, it all splits up into this network of faults called the Marlborough Fault System. We've got the Wairau, Awatere, Clarence and Hope Fault. Most movement from the Alpine Fault is transferred onto the Hope Fault and onto the Kikurangi Fault. If there's one bit of good news, the Kikurangi Fault ruptured in 2016, so that one's gone. The Hope Fault hasn't gone yet, that didn't rupture in 2016. The Awatere last ruptured, had a big earthquake in 1848, so it's been a very active area. We know quite a lot less about the Hikurangi subduction zone and the hazard that poses. We know less about the past earthquakes on it because it's much harder to study. It's offshore or very, very deep. It's not as convenient to access as the Alpine Fault. But it has a similar rate of movement to the Alpine Fault, about 20 millimetres a year in the southern part, up to about 50 millimetres a year in the northern part. It could have similar or greater impacts than an Alpine Fault earthquake at this location. One key difference is that the Hikurangi subduction zone, when that ruptures, is very likely to generate a tsunami. But when the event happens, when you feel the shaking, you won't know at all if it's the Alpine Fault or the Hikurangi subduction zone. So the same message that we convey a lot of long, strong shaking, get gone and evacuate. If it's the Alpine Fault, it'll feel probably pretty similar to the Hikurangi subduction zone. The Hikurangi subduction zone is very likely to generate a significant tsunami. As I said, there's less known about past earthquakes on the Hikurangi subduction zone, but we do know something, and this is where my job of looking along the coastline comes into it. This little animation is just showing what the earth above the subduction zone does in between earthquakes and then during the earthquake. So in between earthquakes, stress slowly builds up, things slowly deform, and then in an earthquake, parts of the land above it pop up and parts come down, and you get that tsunami generated as well. So I look around the coastline at places like the Wairau Lagoons here in Blenheim, and this is a really, really important site for understanding past subduction earthquakes on the southern part of the Hikurangi margin. So this is an area, this part of Blenheim out here, that goes down suddenly in large subduction earthquakes. Not by metres, what we're seeing is at the most half a metre, so it drops down suddenly by half a metre. So we go to these salt marsh environments because they're very sensitive recorders of those changes in sea level. We go out there with these pretty simple hand coring equipment and take little sediment cores through the sediment of that salt marsh. We look at these beautiful little tiny microscopic sand-sized fossils that are specifically adapted to certain tide levels, and we look at how those change through that sediment. When they suddenly jump and change, it tells us that there's been a change in water level, and that is usually related to an earthquake. So So here's some pictures of some of those cores that we've collected from the Wairau lagoons in the salt marsh. You can see these soils here. They're buried quite deep now, a metre to a metre and a half deep. They're former salt marsh surfaces and they're overlain by this intertidal mud, so that's where the land has dropped suddenly in an earthquake. At this site here, there was also a tsunami sand sitting on top of that soil, showing us that a tsunami came in immediately following when the land dropped. And again, we can tell that's a tsunami sand because it's carrying in all those tiny microfossils from deeper offshore. We can radiocarbon.
About how much time would there be from an earthquake to the tsunami?
Good question. The shortest amount of time is probably about 10 minutes, but it depends on where the greatest amount of movement was in the earthquake. So again, it depends on where the epicenter was. 10 minutes to half an hour. So, the key thing there is that the tsunami would arrive before any official warnings are made. That's why self-evacuation on feeling these earthquakes is so important. We've radiocarbon dated these earthquakes recorded over in the Wairau lagoons at about 500 years ago and 850 years ago. So that's largely the extent of what we know about subduction earthquakes in this part of the Hikurangi margin. We have put together research from lots and lots of coastal sites right along the east coast of the North Island, about 40 or 50 sites. Most of them are going up in earthquakes. Some of them, Hawke's Bay is actually very similar to the Wairau area that goes down in subduction earthquakes. So in total, we know of about 10 earthquakes that have occurred on the Hikurangi subduction zone in the past 7,000 years. This is just the record from the past 4,000 years. So you can see it's not as clockwork as the Alpine Fault. It's less well behaved. It's more irregular. Less certainty from a type of record like this of when the next earthquake will be, because it's not such a predictable pattern. I have been asked this question before. Is there likely to be an earthquake that goes right from the Alpine Fault through one of these faults in the Marlborough Fault system and onto the Hikurangi subduction zone? From a sort of point of view of looking around the globe, we've never seen an earthquake like that. Modelling would suggest it's extremely unlikely, and our earthquake record also suggests it hasn't really happened all in the past few thousand years. So this is the Hikurangi subduction zone earthquake record here, going back in time. This is the Alpine Fault here. So at least in the past 4 earthquakes, there's been no overlap in time between earthquakes on the subduction zone and on the Alpine Fault. They don't appear to happen together. When we add in things like the Wairau Fault, the last Wairau Fault earthquake happened about 2,000 years ago, and there was another one about 3,000 years ago. So again, there doesn't seem to be any predictable or any consistent relationship between these faults. It doesn't appear from the geological record that there's ever been an earthquake, at least in the last 4,000 years, that goes right through.
What about the correlation between like the Kubernetes activity? Does that transfer down to us?
It's too far away.
It's too
Yeah,
far away.
yeah, it's just too far. Which is good, it's very active.
It's very active.
Yeah. What we know about the Wairau Fault and the Alpine Fault is that both models and these geological records show that sometimes they might rupture together. So you might get something on the Alpine Fault going right up onto the Wairau Fault, but that very, very rarely happens. And now, I'm going to hand back to Alice to talk more about preparedness. Thanks, Kate.
So, some of you may have seen this photo before, I'm not sure. This is a house that was sitting on the Kikeringu Fault in the Kaikoura quake in 2016. The story I have heard goes that the guy inside definitely got a bit of a wild ride, definitely got shaken up quite a bit. But the reason I'm showing you this image now is to show you how well our wooden frame buildings actually stand up in these events. Clearly this is not not livable long term afterwards, but in terms of a place of shelter during a large earthquake, it definitely served its purpose. Apparently the guy did, eventually try and step outside in the morning and went to walk outside and realised his path had moved all the way down here. Fell right out the door. So the reason I'm showing you this image now is to talk a little bit about preparedness, talk about a little bit about what we can do, and one of those things is making our homes a bit safer. These are the places we're isolated and we need to be looking after ourselves for a period of time after one of these big events like an alpine fault or if you've had any subduction zone earthquake. This is what we want to, not necessarily exactly like this, but we need to have our homes in a state that we can actually shelter in for a period of time.
Is that a concrete slab home?
No.
Yes.
No.
On piles. So you will all have received, well if you haven't, there will be one around, one of these brochures from EQC. This has got a load of great tips in it in terms of how you can quake safe your home. Encourage you to take a look through that. Thinking about securing some of your heavy furniture, bookcases, whiteware, hot water cylinders, because essentially they have a lot of water in them after these events too. They can be considered part of your water supply. And brick chimneys as well. A few images here. There is a lot of information in that booklet, and I encourage you to take it home and have a good read and share that stuff with your family as well. Some of the other messages and places to go for information around preparedness, if you're not already aware. Ultimately, talking about these events is essential to preparedness. It's the cheapest, easiest, freest way to start getting prepared for them, and that's one of the things that AF8 tries to encourage people to do, is to continue talking about this. New Zealanders are awesome, absolutely awesome, as we all know, in coming together when these things happen. There's absolutely no reason why we can't do these things a little bit ahead of time. Having conversations with your friends, family and neighbours around how we can be better prepared is a great place to start. Making an emergency plan. What are we going to do if we're not all in the same place when something like this happens? How are we going to communicate with each other? How are we going to get back to our loved ones? Finding out where to go for information. Every region is different. The team here will be able to provide you with some of the best places to go in the Marlborough region. But finding out where to go in advance so you know what you're looking for. Household emergency kit. It doesn't have to be a major kit in the corner that you never touch ever again. Having enough supplies around to be able to look after yourself in whatever shape or form is a great thing. And we say prepare enough food and water and supplies for at least 7 days. I've just come back for a week on the West Coast. The messaging over there is, at least 2 weeks. Ultimately, whatever was in with your capacity to do is a good place to start. And I'd just like to say, you don't have to do a lot of this stuff on your own. We are good at coming together after events. Pooling your resources before an event is also a great idea. My parents live over in Tasman. They moved off the farm recently and they took the generator with them to Wakefield. And they told their friends, they told all their new neighbours, hey, we've got a generator, this is what, our daughter works with the AF8 project, If you want to you guys don't all need generators as well, but perhaps if we all pull a little bit of fuel, then we have something together. Maximise your resources by working with others. Take steps to quake safe your home. Get aware of go bag. If we've got tsunamis, long, strong, get gone. What are the things that you want with you when you have to evacuate? Have them handy. And just like you're doing tonight, find out about natural hazards in your area and share that information as widely as possible. The more we talk about this, the easier it is to get prepared. There's a few websites here as well. Get Ready, the National Emergency Management Agency's resource around preparedness. EQC has some awesome resources on their website about being prepared, particularly around your home. Neighbourhood Support, who are here in the room, have some awesome resources about bringing your community together. And I think they also use the Gets Ready app in this region as well, which is a great way to sort of register your skill set and your resources, so they might be able to be helpful for other people in the future as well.